Hello everyone, myself Dr.P.Vijayakumar, Associate Professor, Department of ECE, Aditya University. In this session, we are going to see discrete random variables applications. So, the types of discrete random variables, binomial and Poisson random variable. At the end of this particular session, we will be getting two learning outcomes. One learning outcome is applying the binomial random variable concept for solving the real-time problems, and the second learning outcome is applying the Poisson random variable concepts for solving the real-time problems. So, first one is binomial random variable. So, binomial distribution. So, when do we say a random variable is a binomial random variable? So, when a trial is performed, it consists of only two possible outcomes, and the trial is repeated many number of times, and it consists of either success or failure or defective or non-defective, 1 or 0, yes or no, and the same experiment is repeated multiple number of times, and the events defined on that binomial events defined on that random variable are independent, then those trials are called Bernoulli's trials. So, under Bernoulli's trials, so whenever the experiment comes under the category of Bernoulli's trials, we can apply the concept of binomial random variable. We can assume by default it is a binomial random variable. An example is tossing a coin in an experiment where outcome the results are heads and tails only, and the coin is tossed multiple number of times. So, another example is the condition of parts in a machine may be categorized defective or non-defective. So, the probability mass function of a binomial random variable is defined as probability of x is equal to x, NCx, p power x, 1 minus p whole power n minus x, where n is the total number of trials, and x is the number of times it is success, and p is the success probability, and 1 minus p is the failure probability. So, this is the probability mass function. In a similar manner, using the probability mass function, the binomial distribution function can be written as summation k nck p power k 1 minus p whole power n minus k u of x minus k, and the density function can be written as fx of x is equal to summation nck p power k 1 minus p whole power n minus k del of x minus k. So, the applications of binomial distributions, many applications are there. Here we are mentioning only few applications, any games of chance, and the signal detection in radar and sonar systems, and quality control to classify the items as defective or non-defective. So, these are some familiar applications. Along with this, so many applications are there. Any application which is related to Bernoulli's trials, we can apply the binomial random variable concept. So, let us see one example related to the binomial random variable. So, given a random variable x is having a binomial distribution, the total number of trials is 8, the probability of success is 0.5. Now, we are asked to compute the probability of x is equal to 4. That means, x is a random variable which indicates the success 4 times success out of n trials. So, 8c4 p power 4 is 0.5 whole power 4, 1 minus p, 1 minus 0.5 whole power 8 minus 4. So, when you solve this one, we will get 0.273. So, we know the NCR formula, n factorial by n minus r factorial into r factorial. We need to apply this formula for computing 8c4. So, the value we will get is 0.273. Similarly, one more question is asked, probability of x less than or equal to 2. That means at most 2. At most, the maximum value is 2. That means probability of x is equal to 1, probability of x equal to 2, at most 2. So, the same formula again we will apply, NCR p power r 1 minus p whole power n minus r. Applying the same formula, we will get this one. So, substituting both values, we will get 0.14063. Next one, probability of x greater than or equal to 7. This is probability of x is greater than at least 7. At least 7 means minimum value is 7 and the maximum value is Here only number of trials maximum are 8 trials, the maximum value will be limited to x is equal to 8. So, calculating both values and adding we will get 0.0351, 0.0351. If we want to compute the probability between two values, 3 to 5, 3 is included and 5 is not included. So, probability of x is equal to 3, probability of x is equal to 4. Applying the formula, we will get 0.2, adding both of them 0.492. Okay. Let us see one more problem. In 256 sets, out of 12 tosses of a fair coin, how many cases we can expect? 8 heads, 4 tails. So, if 8, so total number of trials are 12. So, the probability of success will be 1 by 2. The probability of failure will be also 1 by 2. Number of times the heads, x is equal to 8, that is 12c8, 1 by 2 whole power 8, 1 by 2 whole power 12 minus 8. So, we will get 0.12. This is for one set. He is asking for us to calculate for 256 sets. 256 sets and the chances multiplied, we will get 31 times, we will get the success. 31 times, we will get the success out of 256 sets. Next, one more problem which is related to binomial random variable. So, a family consists of 5 children, totally 5 children. Among them, 3 are boys, 2 are girls. The probability of boy is 1 by 2, girl is 1 by 2. Why? Because if nothing is mentioned regarding the probability, we need to assume them as equally likely or equiprobable events. If nothing is mentioned regarding the probability, we can assume by default them as equally likely events. Only 2 possible in a family, boy or girl. The probability of boy is 1 by 2, the probability of girl is 1 by 2. Now, they are asking us to calculate the probability x is equal to exactly 3 boys. X is equal to exactly 3 boys. So, 5c3, 1 by 2 whole cube, 1 by 2 whole square, 0.3125. Okay. Next problem is related to the factories, machines. A machine produces 10% of defective items. For every hour, the mechanic draws a sample size of 20 for inspection. So, a machine is producing 10% to defective items. So, during the production, for every 1 hour, the mechanic takes some samples of 20 for inspection. If the samples contains no defective items, the operator does not stop the machine. What is the probability that the machine will not be stopped? So, but how much amount of time the machine will not be stopped? This is the chance we need to calculate. So, samples collected by the mechanic is 20 samples and the probability of getting a defective item during the production is given as 10%, that means 0.1. The probability of getting a non-defective item is 0.9. Now, we are asked to calculate what is the probability that the machine will not be stopped. That means, no defective item should get. The probability of x is equal to 0 will be 20c0. So, here defective item is the success. Defective item is the success, we assumed 0.9 whole power 20. So, 0.1216. That means 12.16% of chance is there for the machine not to be stopped during the production. But there is more scope for stopping the machine. 12% means around some 88%, there is more chance to stop the machine because it is producing 10% of defective items. That is the main reason. So, the next discrete random variable we will see is Poisson random variable. So, there is a minor difference between a Poisson random variable and binomial random variable. Both you can apply for the cases of Bernoulli trials. So Bernoulli's trials, during Bernoulli's trials period, you can apply Poisson random variable also, but while applying the Poisson random variable, we need to make sure we need to follow some conditions. The condition is n should be a very large value, the probability of failure should be very small. The probability of success is very small and n should approach large. That means n should approach infinity and the probability of success should approach very much close to 0, very much close to 0. In those cases, we need to consider the Poisson random variable applying. So, the Poisson random variable is mathematically defined as there is a parameter called lambda, which is an average value, average or mean value. The probability of x is equal to k is lambda power k e power minus lambda by k factorial. This is the probability mass function for the Poisson random variable. So, using this probability mass function, we can define the density and distribution function. So, the density function is fx of k is equal to e power minus lambda, lambda power k by k factorial del of x minus k. Similarly, the distribution function, the capital PDF is u of x minus k, the density function is del of x minus k. There are so many applications where we apply the Poisson distribution. The thing is, we need to remember that n should be large and p should be small, and the product of NP should be a moderate value. The product of NP is called average value. The product of NP is called average value, lambda. Okay. So, this is the scenario where we need to apply the Poisson random variable. Based on these conditions, we need to apply the Poisson random variable. So, the number of telephone calls arriving at a switchboard during the intervals of time. This is one example where we apply the Poisson random variable concept, and the number of customers arriving at a bank during the intervals of time, the random failure of the experiment, the number of earthquakes occurring in some fixed time span, and also the last example is the number of electrons emitting from the heated cathode during a fixed time period. So, all these are Poisson random variables. Okay. And these are some few examples, very limited examples we can show here, but there are so many applications where we can apply the Poisson random variable concept. So, wherever the need is there, like Bernoulli's trials and the n is very high value, probability of success is very low, all those applications we apply the concept of this Poisson random variable. So, let us see one example related to the Poisson random variable. So, a call center is there which is receiving an average of 5 calls per hour. So, per hour they are receiving only 5 calls. What is the probability that they get exactly 3 calls? So, the number of calls received is per hour is 5. That means the average rate is 5. The average rate is 5. Now, the probability of x is equal to 3. That means exactly only 3 calls. So, e power minus lambda, lambda power k by k factorial. So, e power minus lambda means e power minus 5 into 5 cube divided by 3 factorial. So, 5 cube is 125, e power minus 5 is 0.067, 3 factorial is 6. So, simplifying this, the approximated probability value is 0.1404. So, next problem is also related to the Poisson random variable. People enter a club at a rate of 2 for every 4 minutes. So, that means for every 4 minutes, at least minimum 2 people will enter the club. What is the probability that the no one enters over the time interval 10 pm and 10:10 pm, and what is the probability that at least 4 people enter during that time? So, first we will consider this case. What is the probability that the no one entered over the interval 10 to 10:10 pm? So, firstly the average rate is given as 2 persons are attending for every 4 minutes. Now, we are asked to compute the what is the probability that the no one enters over the time interval 10 pm to 10:10 pm. 10 pm to 10:10 pm means the time duration of interest is 10 minutes. So, the average value will be B is equal to lambda t. This is the average or mean value. Average or mean value. B is equal to lambda t. 2 by 4 into t. So that is 20 by 4. The average value is 5. Now what is the probability that no one enters during this duration of interest? That means probability of x is equal to 0 is e power minus 5, 5 power 0 by 0 factorial. So there is 60% chance is there over this interval. No one entering over the interval 10 pm to 10 pm. The next question is, what is the probability that at least 4 people enter during that time? At least 4 people. At least 4 people means probability of x greater than at least 4, x greater than or equal to 4, at least 4 people. So this can be calculated using the concept probability of x greater than x is equal to 1 minus probability of x less than or equal to x. So the probability of x greater than or equal to 4 can be written as 1 minus probability of x less than 4. That means 1 minus probability of x is equal to 1, probability of x is equal to 2, probability of x is equal to 3. So this 1 minus e power minus 5, 5 power 1 by 1 factorial, e power minus 5, 5 square by 2 factorial, e power minus 5, 5 cube by 3 factorial. So that is 1 minus this value simplified, we will get 0.1352. That means 13% chance is there, at least 4 people will be entering during that time, 13% chance, very less probable chance over that certain time period, 10 minutes time period. So let us see one more example related to the Poisson random variable. So in a country the suicide rate is given as 5 per million people. So million people means 10 lakh people, at least 5 people will be making suicide attempt. So the probability of the success will be 5 into 10 power minus 6 and the average value lambda will be NP, you will get 5, average value is 5. Find the probability that in a city of population of 10 lakh, there will be at most 5 suicides. At most 5 suicides means, at most means maximum 5 suicides. So the probability of x less than or equal to 5. So maximum means here 5 is not included, x less than 5. So the probability of x less than 5, that means probability of x is equal to 0, probability of x is equal to 1, probability of x is equal to 2, probability of x is equal to 3 and the probability of x is equal to 4. So this is can be written as summation k is equal to 0 to 4 e power minus lambda, lambda power k by k factorial. So here average value is e power minus 5, 5 power 0 by 0 factorial, 5 power 1 by 1 factorial plus so on 5 power 4 by 4 factorial. Calculating all these and multiplying, we will get 0.4404. So this is the chance, 44.04% chance is there for getting suicide of 5 per 1 million, 10 lakh. And one more problem which is related to the lottery tickets, a game, okay. Lottery tickets, suppose you buy a lottery ticket in 50 lotteries, in each of you the chance of winning the prize is 1 by 100. That means probability of success is 1 by 100 and total lotteries are 50. What is the probability that you will win a prize at least once? At least once means probability of x greater than or equal to 1. That means 1 minus probability of x is equal to 0. So p of x greater than or equal to 0 means 1 minus p of x is equal to 0. So no time you win the prize, probability of x is equal to 0. 1 minus this value, 39.35% chance is there. The probability of getting exactly one price, exactly one price. So, e power minus lambda by lambda power k by k factorial. Next, at least twice. At least twice is the probability of x greater than or equal to 2, 1 minus probability of x is equal to 0, probability of x is equal to 1. So, calculating this and simplifying, we will get 0.0902. So, very less chance, 9% chance, the probability of getting exactly more than 2 prizes. Getting one prize is 30% chance. Getting more than one prize is 39.35% chance. So, in today's session what we have seen is, we have seen two different random variables which comes under the category of binomial random variable and Poisson random variable. So, firstly we defined what is binomial random variable, we have seen few applications and we have solved some real time problems related to binomial random variable. In a similar manner what we have done, we defined the Poisson random variable, we defined the probability mass function, density function and distribution function for Poisson random variable. Later on what we have seen is applications followed by real time problem solving. So, in the next session what we will do is, we will solve the problems related to the continuous random variables. We will see Gaussian, exponential and uniform. These are the three continuous random variables which we will see in the coming sessions. Thank you.